Greetings from Blacksburg, from the eastern part of the United States. I'm sorry I can't be with you today. I have an INCOSE board meeting in Boston. Hopefully I'll be with you next year. In the interim, I wanted to take some time to discuss with you the journey beyond MBSE. There's no doubt that we are all making the journey to a model-based systems engineering profession. The question is what lies beyond. And to understand what lies beyond and to get there effectively, first, we have to make the transition to MBSE. We have to leverage it in our organizations, leverage it as a profession, and then we can look beyond. So first, let's look to the challenges that we must respond to as systems engineers in today's world. Vision 2025, published by INCOSE last year, did a great job of laying these out, but there are 6 challenges in particular that are highlighted. I tend to speak about 5 of these. First, mission complexity continues to grow, as does the complexity of the technologies that we deal with. As much as we would like to think differently, we know that system design still emerges from pieces rather than from deliberate architecture. Our systems are often brittle, difficult to test, complex, expensive to operate. Exactly the difference of what we would like. Knowledge investment are lost to project lifecycle boundaries. That means individual projects are less effective and efficient than they should be. Worse than that, we don't learn. We don't learn within organizations. We don't learn across the industry. Knowledge and investment are lost between projects. And fifth and finally, as much as program managers and systems engineers should be in it for the same thing, which is satisfying customer needs in an effective and efficient manner, program managers often focus on budget and schedule, systems engineers on technical figures of merit, and we conflict more than we collaborate. These are the challenges that we face, but the challenges are more than that. Certainly, systems engineering evolved from a military aerospace background. Electromechanical systems, top-down, long-lived, stable technologies, stable requirements. This is not the world that we live in today. Now, we have systems engineering practiced in aerospace and defense and well beyond, in medical, in transportation, in energy, oil and gas, organizationally. No longer is electromechanical the implementation of choice. In the 90s, it was software intensive. Now we've passed through to cyber physical. And certainly our systems are not standalone. We have passed through the phase of interconnected systems and now live in the era of Internet of Things or Internet of Everything. So what does model-based systems engineering, what does systems engineering have to respond to? We have to respond to a diverse environment, from aerospace and defense to electronics to automotive to energy to transportation. We have to deal with cyber physical systems. We have to deal with interconnected systems. Most of our engineering is middle out or bottom up. We are engineering into existing brownfield environments. The lifespans of our systems are varied from months to a century or more, and there's the ever-present change in requirements and technologies. This is the challenge that we must face. So, how does model-based systems engineering help us face that challenge? How do we make the journey to good model-based systems engineering so that we can then look beyond? Well, I think we've all seen this chart. It's a classic INCOSE chart that describes the practice in transition, the move from document-centric practices to model-centric practices. It's a great chart, but it's one that has built up a lot of myth and mystique over time. I think the first step to an effective journey is to clarify, is to remove some of that myth and mystique, then clarify, identify a few roadblocks, and then we can move forward. So myths and mystification surrounding the journey. First and foremost, it's the myth that models are new. Nothing could be further from the truth. That was never intended to be communicated. Models have always been there. They are fundamentally central to engineering. Where were they before? They were often in the mind of the chief systems engineer. So the theory, the change in model-based systems engineering is changing from low fidelity representations, captured in documents, captured in specifications, to higher fidelity communications. That enables communication and it enables analysis. So it's not that models are new, It's that we are presenting them, representing them, communicating, and analyzing in higher fidelity ways given the technologies that we have available. Documents aren't going away. As systems engineers, we communicate with a very broad range of people, and documents are a wonderful mechanism for doing that. As we make this journey to model-based systems engineering, we need to be careful of several traps. First, there's the misconception that a series of diagrams is model-based systems engineering, that SysML somehow equals model-based systems engineering. That's not true. Certainly, if you take mechanical engineering and do top, front, side, well, if those three diagrams are connected and coherent, then they can represent a model. But if they are three random diagrams, they represent nothing. The same is true in systems engineering. That's not a statement about SysML. It's a statement about the separation between views and the real model. Secondly, we've all done modeling and simulation in systems engineering. Models in systems engineering is different than model-based systems engineering. Model-based systems engineering requires integration, connectivity, and coherence. That's absolutely essential for us to meet these challenges. And so where does that leave us with views? Well, we need to view, to think about, to analyze, to communicate on our systems from many different perspectives, from requirements to behavior to architecture, from test, from a low level, from a high level. Views allow us to construct, communicate, and analyze these models from multiple viewpoints. We also need to clarify, within INCOSE, when we speak about model-based systems engineering, we typically speak about the model on the left, models that we represent with SysML diagrams. This is the so-called conceptual phase or architectural model for systems engineering. This takes us from concept of operations through test. This is where innovation occurs. This is where resiliency is built in. This is our one chance to manage complexity. But when we talk to those in other domains and we use the phrase model-based systems engineering, they will often think of analytical models, physics-based models. This is where rigor, efficiency, and effectiveness come in. Which of these is model-based systems engineering? The answer is both. For any system of interest, there is one architectural model. It's not meaningful to speak of a requirements model separate than an architecture model. There's one architectural model. The analytical models then hang off of the architectural model. The architectural model is what gives us coherence. For any given domain, we use different analytical models, but we need to recognize that both are here. So with that clarification, then what about the roadblocks that are stopping us? Well, we won't talk about all of these, but I think any of us who've tried to deploy model-based practices have run into some of these roadblocks. First, MBSE requires SysML or UML or UPDM or UAF. Absolutely not. Those are particular notations that may help us internally as systems engineers, but what model-based systems engineering requires is models at the forefront and coherence and connectivity and integration. We're already doing modeling and simulation. We're already doing SysML. Great, keep doing it, but again, coherence, integration, connectivity. We must implement both the architectural and analytical aspects to get any benefit. Not at all. It depends upon what you're trying to do. If you're dealing with a brand new unprecedented system, you're going to do far more architectural work because that's where innovation occurs. If you're doing product line engineering, the 2017 Ford Mustang versus the 2016, you're going to work far more in the analytical space. It's too complex. Not if you realize that models have always been there and we're simply moving to higher fidelity representations. We have to model everything, and it's not possible to model everything. Well, the second half of that is absolutely true, but we don't have to model everything. We need to model across to get a top-level architecture, but then we model in depth where unknowns reside, where risk resides, where we deal with low technical readiness levels. It's a technical problem. It's not a technical problem. It's actually a culture change, organizational change problem. MBSE is the answer. It does everything. It's not the answer. It's a tool in our toolbox. Nothing more, nothing less. It's a very important tool to deal with complexity, but it's only a tool. So with that, If we go back and look at the challenges, what does that enable for us? Well, it certainly enables dealing with complexity in a much better way. Model-centric methods give us far more leverage over complexity than document-centric methods. It lightly touches system design and architecture in better ways. It lightly touches knowledge and investment maintenance at project lifecycle boundaries. But we have not really solved these problems yet, just in that lightweight transition. So how do we really plot the journey beyond MBSE to begin to leverage MBSE for ourselves and our organizations? We will use the key along the right to try to highlight how we can apply model-based approaches to better address these challenges. Well, first, model-based approaches enable reference architectures in a much better way than document-centric approaches. I work with Northrop Grumman on a number of programs. Northrop Grumman does UAVs. They do fixed-wing UAVs, they do rotary UAVs, they do subsea UAVs. They do sensing platforms, and they do weapon delivery platforms. Northrop Grumman was doing model-based systems engineering to design these systems, to architect these systems, and one day they realized that all of these systems have a very common reference architecture. So they took the time and made the effort to step back to abstract that reference architecture. Now that gave them 4 key benefits. First, for a new project that came along, they were much quicker to respond. They did not have the blank sheet of paper problem. Second, they had much more coherence and alignment in their designs. That helped them greatly. Third, they had more coherence in their technical implementation, their particular technologies. That lowered the cost. Fourth, they had alignment across their team. Their team could communicate better. They could actually learn. They could feed the lessons back into the reference architecture and make each generation better than the one before. This is much more possible because of the granularity, because of the richness of the representation. It allows us to deal with complexity, have better design across our systems. Individual projects are more effective, and we can actually learn within the organization. Taking that a step further, we can recognize product line engineering. Most of us live within product line organizations. We do one particular domain, one particular field. We often forget that and want to drop back to brand new innovation, brand new design. That's not really the world we live in. Now, if you live in the military and aerospace domain, the cycle time between projects, between next generation fighters, destroyers, submarines, is long enough that product line concepts simply do not make sense. But if we live in other domains with 2, 3, 4, 5-year cycle time or less, product line engineering enables great efficiency. Where can we take the best of? We can take it from software. We can take it from automotive. We can take it from transportation. This is a step beyond reference architectures because we are innovating in narrow spaces, but we are always bringing greater analytic and rigorous effectiveness, efficiency tools. Helps us with complexity, design, individual projects, and again, cross-project learning. We must move from top-down thinking, whether it's in reference architectures or product line engineering or new innovation, and realize that we don't have the time or money to build everything at the atomic level. We have to embrace reuse and composability. If you go to Google and if you look at how they do new software programs, they don't write single lines of code for every new aspect. They assemble, they reuse, they compose from code modules. We need to figure out how to do that in systems engineering. Systems of systems engineering is a step in that direction because it focuses us on larger building blocks, on bringing existing pieces together to deliver new capabilities. How can we do that at the systems level? It's going to require a different attitude towards integration because if we do it wrong, then we're back into simply assemble it, test it, and fix everything in integration and test. We know that's a very expensive way to operate. but we must figure out how to embrace reuse and composability. Lastly, we need to connect across model-based engineering. And that reflects not only communications, but semantics and syntax. I noted earlier the architectural model and the analytic model. We know that within a project team, we communicate across a broad range of people, from the customer to the stakeholders to the users to the systems engineers, software engineers, subject matter experts. Systems engineers serve as the technical glue to connect those insights, and we serve as the communication glue across that program. The same is true for the models that we use. The models that we use must serve to connect across this span, both analytically and communication. That enables us to bring the best of all these practitioners to the solution of the problem. These are all things that we can do within our organizations, within our projects. There's one more, and that is to apply the concepts that we know as systems engineers to the way we deploy model-based systems engineering. Oftentimes, we want the big win. We want to go after everything at once. We try to tackle all the benefits that we see from model-based systems engineering and deploy them simultaneously. That's not an effective way to implement change. To implement change, we should use our systems engineering concepts and draw a boundary around the system of interest. What's the system of interest? It is our change agents. It is the project that we want to undertake and the benefits that we are trying to get. Once we draw the boundary around that, we need to look at the existing interfaces, and we need to honor those interfaces in data content and in format. That may make us a little less effective within our system engineering effort because we are tailoring to other people's needs. But the reality is that makes the system of change far more effective and more efficient. Your change agents are inside, they live in a black box, you can do anything that you want to there. Once you've proven success, you can slowly expand that system boundary to deliver more value to the organization. But we must engineer our deployments of model-based systems engineering. With that, we then shift to things that model-based enables but live beyond the bounds of any one organization. We can't do them as individual units ourselves. We have to do them as a profession. First is remembering that we are trying to evolve our capability as a community. It is not about evolving and advancing how any one organization performs systems engineering. It's about how we as a practice and profession move from ad hoc processes to institutionalized practices so that new graduates are fully trained in these approaches, that these are our processes, our methods, our tools. We recognize that we are in the mid-stage here. We're looking at architectural models that are more highly integrated with analytics, simulations, visualizations. We know theory, ontology, and formalism have far to go, and then distributed, secure model repositories, etc. This is the journey map for our profession. Well, looking at that journey map beyond the bounds of an individual organization, model-based absolutely enables analysis, learning, and more. We've talked about communication, but learning comes from smaller knowledge nuggets. We have granularized our knowledge in better ways. How does this help us at a broader professional level? This is the Rosetta Stone. We earlier spoke about communicating across a project team. Well, this is true about communicating across professions as well. How about learning? How do we exchange lessons between aerospace and defense and transportation and medical and energy and consumer devices? Each of these domains has their own language. The Rosetta Stone at an industry level can help us translate between. It can also help us unify our profession. Our profession theoretically is one about holism, but we have fragmented in those focused on process, those on management, those on soft systems, those who want to treat model-based systems engineering as if it's something different. We need to use models and our language and our ontologies to unify us, but we also need to use them to learn. because we need to granularize our knowledge. Why is that important? Well, if we go back to good old Clippet in the 90s could have knocked on our screen and said, hey, it looks like you're trying to write a requirement specification. Can I help? Now, Clippet never said this, but what this harkens back to is the data capture aspect of systems engineering. I think we've all from time to time been told, you guys just produce specifications. That's the data capture of what we do. And that's absolutely essential, but there's the analytical aspect of what we do, and that is harder and harder with more complex systems. If we can bring heuristics and wizards to bear, heuristics are lessons learned across cumulative knowledge, then we can have Einstein knock on our screen and say, hey Dave, it looks like you're trying to achieve 5 nines of reliability. Would you like me to help? Hey Dave, that looks like a pretty bad allocation. It's overly complex. Would you like me to help? I absolutely would like you to help. And this is only possible if we granularize our knowledge, bring big data techniques to it, and move forward with heuristics and wizards. That's absolutely possible. Now, my friends in academia always stop here and say, Dave, you're shooting too low. Heuristics and wizards are primitive techniques. They may be primitive techniques, but they help us today. Looking beyond this to what can academia do for us, we look towards supporting theories of systems engineering. Once upon a time, we spoke of the unifying theory of systems engineering. I think we will get there one day, but we've recently changed our focus to realize that many theories already exist that underpin what we do. Decision theory, game theory, complexity theory, control theory, behavioral economics, organizational theory. How can we connect these and their model-based foundations to better inform and execute the systems engineering process? Absolutely possible on a broader level. Those are things that we can do as individual organizations. Those are things that we can do as a profession. So that brings us to what lies beyond. In answering this question, I always like to look to our colleagues. What came after model-based mechanical engineering? What came after model-based chip design? The answer is mechanical engineering. The answer is chip design. These processes, methods, and tools are fundamentally embedded in those professions such that they become enablers, facilitators, but not the focus of interest. I think the same is true for systems engineering. What lives beyond model-based is just systems engineering. But there is one other thing if we do it right, and that is enabling model-based engineering. Systems engineering is the last of the professions to make the journey. This is the model-based engineering lifecycle. This is what delivers radical advances in quality, time to market, cost reduction, everything that we would like. Systems engineers sit right up front and they connect the customer to the overall lifecycle. Now, whether you believe we can get through additive manufacturing and direct to code to the point that we can push a button and produce an automobile or a fighter one day, or maybe we just seek to connect our analytical models, there's great value regardless. But this thought model is absolutely critical because there are two ways that we can make the journey to model-based systems engineering. The first is very inward looking, optimizing our methods and techniques. That's what we've been doing for the last 10 years. We know that optimizing a component does not optimize the overall system of interest. The second thing that we can do is look outward and try to optimize the system. How do we make the journey to model-based systems engineering such that we enable model-based engineering and the overall life cycle that we want? This is how we need to change our focus. We need to focus less on ourselves and more on enabling this cycle. So where does that leave us? Beyond model-based systems engineering, we return to a focus on systems engineering. We allow the model base to fade into the background and become a tool. Now, the journey itself is very, very important. As this fades, what are we left with? Well, we are left with a richer toolbox for communication and analysis, scalable, tailorable practices, heuristics that enable the execution, reference architectures that are more valuable for us, composability, rigor, insight into efficient frontiers, toolboxes of theories that support systems engineering, higher value, and progress. The journey is very, very important. Model-based is necessary to face the challenges of today and tomorrow, but we need to move beyond our obsession with model-based. We need to stop focusing on that aspect and once again, focus on systems engineering. That is the destination that we need to strive for. With that, thank you. I apologize that I can't join you for questions and answers. I hope you will follow up offline. I would love to hear your thoughts and your questions. Best wishes for a remainder of your systems engineering workshop.
Okay.